Maybe we'll get started and let others join us. Uh, Thank you for joining and not like going off for a walk or dozing off. So I hope we can keep you awake for the rest of the sessions. Next talk is by, actually before we announce the talk, there is one request. So there's a Dropbox kept here to drop your these badges. So because unless you want to take it as a souvenir, these lanyards, if you want to return it, you can drop it there so that we can use it for our next event. So next talk is by Jaideep Sen. Vijay is not here, right? Okay. And Pankaj Dayama. Jaideep is a senior research scientist at IBM Research and manager of speech and NLP technologies. He primarily works on question answering and related NLP technologies and is currently engaged in cutting edge research on robust neural retrievers. He has 20 plus papers in top conferences. And the speaker is Pankaj Dayama. He is an IISc alum. He is a senior technical staff member at IBM Research. He leads the AI for Industry Solutions group at IBM Research Labs, and his current focus is in developing advanced techniques for time series analysis tailored specifically for industrial applications. He has worked as a research scientist at General Motors R&D earlier, and uh, he has done his master's and PhD here. Okay, so over to you, Jaideep and Pankaj.
I know. Sure. Is it fine? How do I know? It's fine now? Working? Yeah. Okay, fine. Thanks. Okay, so let's begin. I'm going to talk about IBM Granite, trying to cover concepts, models, and usage. Now, first of all, like if I try to really code the technical report that we released out of IBM Granite 3 release statement, so this is how it reads. Like IBM Granite 3 is a new set of lightweight state-of-the-art open source foundational models ranging from different parameter size. And the figures that you see is there from the base models, instruct model. These are some of the results we will review. But if I just start from here and try to work backwards, some of the things that we definitely want to know while we go away after this talk, what is this typical terminologies like language models, how it evolves to foundational model, and how does it really come to this point where we are better than our competitor models so that we can appreciate the journey. So I'm going to briefly talk about these stuffs, language models, LLMs, their evolution to foundational models. I will talk about Granite suite of models. I will cover the language and code where Pankaj will be covering the time series. I will pick retrieval augmented generation as a particular use case. And I will show how you can use Granite models off the shelf with existing technologies with almost like minimal codes to build your applications using Watson extra AI. Okay. So let's try to go towards path to Granite, try to figure out how it really evolved. So first of all, what is a language model? Typically, as the name suggests, it's an AI model which statistically tries to model the sense of language. Now, what does this mean, the sense of language? It just typically tries to assign a probability to a collection of tokens in order to say that this particular sequence of token, does it constitute a valid sentence? Is it a valid language sentence or not? And turns out if you are able to do that, if you are able to differentiate that between these four sentences, how the partial ordering of the probability looks like, then you have a good sense of language. Then you know how to speak like human speaks language. That's the definition of language models. Now, predominantly transformers have been taking over this language model in all of the most of the NLP space from 2019. I'm not going to go into the technical details. Just keep this in mind that it's a block of encoder blocks and then a decoder blocks with a cross attention in between them. We will just need to remember this figure because when we discuss MOE, we will see that how the attention blocks here changes to facilitate mixture of experts. And typically, if you want to, let's say, fine tune such transformer blocks for a particular end task, what you are essentially doing is you essentially try to take an embedding for encoder models, or if it's a decoder model, you will do like this next token prediction, like my colleague Padmana was showing. But you essentially try to tune the whole thing. That would be the traditional way of doing things. You tune the whole param layers for your particular task. Now, this is where the things starts interesting. Fast forward today, when let's say BART base was there, which was a game changer at its own time, it was just having 12 layer with 110 parameters. And today's GPT-3 has 170B parameters with 96 of such layers. Obviously, such kind of architecture is going to be much more hungry of tokens. So earlier days, it was like 30B tokens, and now even 300B tokens is like only less than half of an epoch. And needless to say, it kind of rakes up a lot of volume towards computation. It's computationally expensive. So if that is the case, the question that we want to ask ourselves is, why are we still using LLMs at all if this is that much expensive? And if you're trying to answer this question, we will also partially have the answer towards what can we expect from Granite, because this is ultimately coming from those philosophy of models. So the interesting thing that really worked as a magic, or kind of what glued everyone towards studying large language model, is this emergent zero-shot learning, which was first shown by GPT-2. What it turns out is, if you are able to formulate your task in a way which almost seems like a normal completion task for the LLM, which it is already trained for, then it can do the task without needing any tuning at all. So for example, if you're trying to do a question answering, you give a passage, you show a question, and you say answer colon, it almost fills up like it has seen in its pre-training. And that ability to do it without needing tuning is what got everyone interested. Like that was a game changer. And turns out GPT-3 even moved one step ahead. It said that in it, you can even show it how it is to be done, and it can figure out those clues to do the task itself just by in-context learning. And it's not just some anecdotal examples. It literally competes well with fully fine-tuned model. And this is where you get a sense that the language model towards large language model, where you are having a lot of these parameters, it starts behaving as a foundational model, because maybe I will borrow the term Pratibha also used. It's more like a sponge. You hit all the data that you have there, it digests all of it. Now all it remains is you need to understand how to tweak that to get the right information out of it. That's what it's called foundational model. And coming to Granite, this is what you would expect out of Granite. And this diagram kind of shows that how Granite stands today compared to other competitor models like Llama or Mistral. And you can see these are across different domains. It's not for a particular domain. It's truly foundation model in a sense, because it is catering to different domains and doing better than competitor models just by the basic foundational model style tuning that it has had. Padma did talk about prompt tuning. I won't go into detail, but there are different ways of tuning this model, because obviously you can't keep on tuning all the parameters. So you tend to do soft tuning, like you freeze the model, but only tune certain parameters of the prompt such that it adapts towards a certain task. And that also the community, it's a well known to the community that prompt tuning works quite better. It gives you task versatility. Sure. So let the model figure out. Model can understand. Yes, yes. And actually literature shows that you are not really losing out anything. If you are doing good in prompt tuning, it will easily get the same performance as if the model was fully fine-tuned, which was again a deal breaker. Now, the other thing I want to talk about, so that we can appreciate the difference between base model and instruction fine-tuned model in the Granite suite of models, it's instruction fine-tuning. So again, what's the need of instruction fine-tuning? So typically this intuition that, oh, you need to spell out the task such a way that it almost feels like auto completion for the model. this doesn't fit the bill for all the tasks. Because again, language modeling may not be same as trying to assist user for a user initiated task. This is an example, like explain the moon landing to a 6-year-old in a few sentences. It is not something you can easily tweak towards from the model, and model will give output like this. So this is the usual model output without instruction fine tuning. And the way to solve it is you actually give how it is to be done. You actually produce the gold standard data. So in that sense, it is going towards fine tuning, but it is still not fine tuning. Why it is called instruction fine tuning? The reason is, in a traditional fine tuning, you will take a task, you will give off a lot of instances of that task so that it learns the task. Here, the idea is I don't have that much label data. I am actually going across the task. I'm trying to generalize across the task so that the key learning happens, that the model can associate what kind of instruction, how it is to be parsed in order to produce the right output. And this is an example which also nicely illustrates how it is done. So if you really see, there are two different questions. Answer the following question by reasoning step by step. It is more of asking for a logical explanation, right? And if you are training via this paradigm, the part over above the dotted line, during the inference time, it easily understands to an unseen instruction how it is supposed to behave, because it has learned the correlation, how to understand human instruction and behave like that. So that's the instruction fine tuning. And when put to granite models, instruction fine tuning for granite model, again, it supersedes Llama or Mistral counterparts. And if you also see the type of task we are trying to deal with here is slightly different than the base model. These are the tasks where you typically need someone to come and guide the LLM that this is the task that needs to be done. For example, function calling, putting safety guardrails, like giving a prompt that don't use this kind of language or don't put out this personal PI information. So these are some instructions that you typically tend to give the model so that the model respects it. And this diagram that you see, these tasks are more closer towards those tasks that will leverage instruction fine-tuned model. Okay. So now, if I kind of take you towards Granite 3.0 suite of models, the full documentation is available here. You feel free to go check out. There are more details there. I'm just trying to take snapshots and give you the key highlights. So IBM is trying to basically really build the foundation model across different use cases. That includes language, code, chemistry. Pratibha was talking. There is time series that Pankaj will be talking about. Geospatial is also Pratibha covered to some extent. So if I focus on language, so what language models can be used for? These are just some examples. It's no way an exhaustive list. You can do it for search. You can do it for generating content, the typical completion stuff, information extraction, or translate to different languages. The key point that we do highlight, and it's kind of a strength that we identify within IBM, at least here, is, so the foundational model, they have literally seen everything that is out there in public domain, at least the models which are quite big in param size. But even all the data that is there in public domain, it's hardly 1% of the actual enterprise data is represented there. So if you are trying to use a model that is really usable in enterprise use cases, for example, RAG kind of thing or agent modeling thing that Dipti will be talking about, you want to see more kind of data that is really enterprise grade data. That's where Granite excels. So here the key vision is, let's say you start with enterprise document, which is not there in public domain. It's not something that you can readily reuse the knowledge in the parametric knowledge base of the model. And still you want to excel on the task on those enterprise documents. There Granite will be having an edge that we will be seeing via the numbers as well. So this is again the snapshot of the paper. If you remember, I started the first slide with this comparison, base models and instruct models. And these are the set of models that is available as part of the Granite suite of models. And if you really see here, there are predominantly three different categories. The base category of models varying towards the size 2B and 8B. Then there is the instruction fine-tuned models. I just described what's the difference between base and instruction fine-tuned models. And then there is this MOE mixture of expert type of models. The 400 or 800 typically means how many activation experts are really there, how many activated neurons, I should say, are there in those models. And I will just talk about a bit what I really mean by what mixture of experts. So talking about the 8B or 2B instruct model. So this is our IBM's internal dense architecture, which is in this foundational model stack. There is state-of-the-art training and data recipes, and much to its credit should go to that Shailaja did present that data prep toolkit, right? So it is very important to know that the data cleaning has really helped us here, because we need not see so much tokens that typically Llama or GPT-3 needs to see. We have trained 12 trillion tokens, and this data is strategically generated to be more enterprise friendly, or towards uh, facilitating those applications where you need more enterprise data or interaction. It might be RAG, summarization, or in terms of code, generating code, or even uh, generating follow-up comments on code or fixing code, the agentic use cases, multilingual support. These are the strengths of the Granite models. Talking about mixture of expert, what really happens is, if you remember the initial diagram that I showed of transformer, the typical feed forward layer after self attention. So the idea is, I will just try to stick with the intuition so that you can at least figure out how where the appeal really lies. So here the idea is, instead of a single feed forward neural network, I would almost view it like I want to split the entire network into multiple parts, each part behaving like an expert. Now, what do I get out of it? The benefit really is, if I am training in such a way that I learn to know which expert to pick for a specific task or specific part of input, then at inference time, I am no more using the full network. So the huge benefit it offers is, it almost gives you an expanded capacity, but at runtime, only a part of experts are getting used, which are learned during training. So it hugely brings down the inference cost. And that immediately basically tells in the model of Granite MOE architecture. So these are basically some of the model which at runtime, this can even operate at less than 1B parameters. And that has minimal performance trade-off. It doesn't really perform much more than the full model, which is not having MOE. And this is also therefore becomes the ideal choice if you're trying to drive on-device application or on-prem applications. Now, this diagram, if you see, these are base models and instruct models again, and all of the results that you see, these are across different domains and across different tasks. So the key point to remember here is, this is not some one-off data sets. If you are even having 1 or 2% gain here, that means it's a significant thing, because it is getting averaged out across domains and tasks. And these are just kind of those consolidated reporting. You will get the full things in the paper that I have showed the link here. Now, if you see Granite in the base models, Granite 3B easily beats Llama model and Mistral model also, Granite 3.8B, Llama and Mistral. Same for Gamma, it does beat Gamma model. The other important thing to notice here is the pattern is same for the 3B models also. Even for the smaller model, Granite is better than its competitor. And the point that I raised, if you see the 400M or 800 M models, which is a mixture of expert models, you don't really lose out too much of accuracy here. It is still kind of a respectable accuracy that you can work with, and it becomes super cheap to run on your devices. No. This is the accuracy numbers. This is the accuracy numbers. And the similar pattern also holds in the instruction variant of the models. The typical task is, as I was showing in that earlier chart, the different hexagon points that we want to touch here. This is a very famous benchmark specifically for RAG, and because this is on RAG, you are trying to evaluate how good the generation quality is. And the GPT-4 typically uses LLM as a judge. That's the standard procedure of doing things. And there also you see Granite 3 models, Granite 3 2B models and 8B models kind of far exceeds the competitors. Granite here, the 3 2B model at least is better than even Llama 3B model. And 8B model is also better than Llama 8B model to some good margin. Okay, and the other thing I should also mention here is there was specific care taken towards training the Granite models to make sure they are very safe. They are having automatic guardrails built into that. There has been specific care taken about consulting a taxonomy that IBM created together with MIT Watson Lab, where you categorize different kind of risk that can come out of LLM outputs. The risk can be like misleading, can be something like giving some wrong information or information that can induce self-harm. And it basically it tunes towards making sure that those things are carved out automatically. And the way to prove our point is these are some of the data sets which are on safety benchmark. Meaning like these are the data sets which specifically tries to measure that how well you are producing safe outputs. Where quote unquote safe means that it is not coming under the radar of those taxonomies which are the risk categories. And in this case, Granite 3 compared with Llama and Mistral, we can see across the different benchmarks which are for safety measures, we are better, except in alert, we are slightly down. No, these are again all accuracies. Okay, then going into the code models, the neat way of basically trying to induce code understanding in the Granite model is, so this is the path we are taking. So you are essentially trying to have a text to code alignment both ways. So given a text, given a code, you are trying to summarize that to a text, which needs the model to make a good understanding of how code and text together correlates. And the same understanding gets refined, bolsters, or revised depending on you are trying to take this code summary and generate the code back. So this is kind of a full loop which makes sure that the code and associated text gets nicely coupled. And once this happens, you would expect that it would be understanding code as good as language, because ultimately it is trying to align both of them and it's already good in language. And it does show up that by looking at the different kind of code problems you solve using Granite. So it can be generating code, which is like given a command, you are trying to generate a code snippet, or even explaining code, like given a code, you are trying to explain what the code is trying to do. Fixing code, meaning I have a code, I say that, oh, I am getting this error out of this code. It understands what the text is talking about, what kind of error it needs to resolve, and it can go and fix the code. So all of these different tasks typically gets handled by a good code to text alignment, for which we were utilizing that nice cycling loop. And we are very proud to say that in terms of transparency index, again, this is something IBM cares about a lot. We actually were better than Meta and OpenAI in terms of Stanford Transparency Index, which basically stands to say that these are some of the models that enterprise can use. These are not only license friendly, but these are also those kind of models which are fair, transparent, and provide indemnification for to clients for any of the usage. Now we'll move on to a particular application, RAG, Retrieval Augmented Generation. Talking from a motivation point of view, why RAG is so important in nowadays. So let's say if I have an LLM, typically LLMs are so good that if you just throw it a question, it will always generate an answer and more or less almost correct. Now here is an example. Now number of area codes in New Hampshire. If I just give it to a black box LLM, let's say even greater than 100B, I haven't listed the LLM, but this was a real example. The greater than 100B typically means that it's an LLM which is of mighty value. It's not small param, but it still ends up giving you incorrect answer. The way to correct it is you retrieve some documents. You retrieve some document from your corpus. Then you tell the LLM to generate that given this question, these are the retrieved documents, can you generate the answer? Then it corrects the answer to 603 because it has the reference document from which it sees that what the correct answer should be. So that's the importance of LLM, even if the LLMs are becoming mighty, retrieval augmented generation is going to stay as a important topic. Now, in terms of typical framework, this is how one would like to do, right? You try to load your documents. There has to be some splitting so that because every LLM has only a certain context length. And then you try to create an embedding vector out of those documents that you store in some vector stores. And this can be various implementation or instantiation of these vector stores. There are Pinecone, ChromaDB, Phase Index, Elastic, and so on and so forth. And then given a question, you use a retrieval model to retrieve from that vector index the relevant document and create a prompt that tells the LLM that, hey, this is my question, use the retrieve document and generate an answer. This is how the typical retrieve then generate formula works like. Now, at this point, I will also like to mention the IBM embedding models which are there in Watson X.AI, which you can readily use for the retrieval purpose. And in fact, this is getting renamed as granite.embed because you can easily see that how this falls into that granite suite of models more from an embedding point of view. Slate, the Slate is the typical language IBM uses, like the comparison of Granite is Slate for retrieval. So think of it Slate like Granite embed. So all the Slate will become Granite embed, will be renamed. So these are all embedding models. One is 125 million parameters, one is 30 million parameters, and depending on the size, there is always a different, also the differentiation between number of dimensions, the vector dimension it uses to represent a document. And the best Slate model that IBM has today, Slate 125M, Slate 30M, these are trained on 371 million pairs of IBM approved data. Again, IBM approved is an important part because this is license friendly. You can literally use it without worrying about licensing stuff. And it follows a nice strategy towards different pre-training, which is specifically suited for robust embedding creation. And unsupervised followed by supervised fine-tuning training strategy. And this is already better than typical, most of the time used embedding models, All-Mini LM or E5 from Microsoft in BR benchmark. The BR benchmark again is basically a benchmark which is across at least 9 different domains and 18 different data sets. So any improvement in BR benchmark is significant because it's across domains. Now, Watson X.AI for RAG, I'm just going to take you through a quick walk how you can use Watson X models and framework to create a RAG pipeline for your own. So the pipeline, typically pictorially, this is how you looks like. You start with a question, you do search using, let's say, IBM Slate models. You get the documents out of your index documents. You provide an instruction, search result, and the question, that is the prompt to the foundational model, which will be Watson X Granite, and then you get to the final answer. So let's see how easily we can do it. So I have listed down different steps, maybe 8 or 9 steps, but bear with me. I promise you each of the steps is nothing more than 2 or 3 lines of code. It's that easy really. So first is you get an API key for your Watson X access. You get an API key so that you can access the models from there. Then I specifically loaded a particular text splitter from LangChain. You can write your own, or you can just simply reuse any of the text splitter that you like. It's a standard stuff. Then I'm listing down all the different embedding models that I have in Watson X, and you see it lists down this. There is this 125M, Slate 125M model, Slate 30M model is here, and this list is continuing. I'm just taking a snapshot. So you can pick one of the retrievers that you want to use depending on how much cost you want to incur. And that's it. You basically just create an Watson X embedding model. There is already a built-in class for you. You mention that I want to use this 30M English. This is the embedding model that I want to use. You provide the API key, and you set up the chroma. Chroma is the DB store, the vector store that basically stores all your document with the text and embeddings. And you use a Granite 13B chat as your generator model. So retrieve and generate, this is again Watson Granite model that you are utilizing. And you are instantiating this particular model with the different parameters. So I'm using greedy as my choice of generation strategy. Then how many tokens you want to generate if you want to configure that. How do you want to say that I have done generating, it should be end of text. These are all configurable parameters that are easy to play with or tweak with. And then you instantiate the Watson X Granite pipeline with the API key and the typical configurations that you have created using these params. And that's it. You just create a chain. You create a chain just by saying that I'm going to use this instance of Watson X Granite, and I'm going to use this doc store that I have set up with my Slate embedding models. And the chains type stuff means I'm just going to append whatever document I'm retrieving from here to the Granite. That's it. This is a sample document I am showing. This document will be chunked and stored in different representations. Now on this document, after this has been processed, chunked and indexed, let's say I'm asking this question, what did President say about Ketanji Brown Jackson? And you can see this is the particular chunk that the slate retriever model retrieved from you, where you have the relevant information where this question can get answered, and it does consult the relevant information to come up with the result that the president said one of our nation's top legal minds will continue justice-based legacy of excellence. Okay, and all of this stuff, this is kind of the step 9, step 1 to 9, instantiating the slate model, instantiating the granite model, using LangChain to tie them up together. All of them, if you really see, in each of the steps, it's maximum 2 or 3 lines. That's the configuration you are doing. The rest of the things are ready-made for you to use. And I will just pause here because I just took a very particular specific cookbook to show you how easy it is to done. I took the example of RAG, which is here, but there is this lot of these other notebooks across different tasks, including agents, including tasks like entity extraction or function calling that you can just go and play around with. This is the place where all of these are available. Last, I will just quickly list down some of the research opportunities or / these are some of the projects where you can take up or we can collaborate. So one of the easy things is align granite models for specific domains and tasks. And I am purposefully listing a hint here. If you remember, Padma did talk about InstructLab. This is the perfect repo that InstructLab entry point is so easy. Like you just need to give few examples in a taxonomy node. Rest everything in the InstructLab is built in. So it really taking granite model, making some taxonomy node entries into InstructLab, and you can see granite doing better on your particular domain or task. Then trying to have speech plugins for granite. Again, the hint I'm taking is this is one of the, this came the best runner-up paper award in interspeech this year from IBM. SALSA, this is around asynchronous speech synchronization with decoder models. So this is a recipe you can try to think of pulling into granite to make it multimodal. And then this is more of a real research threads, joint tuning of granite model and retriever, where both of them can receive feedback from each other and tune each other better. The work I would refer is GritLM, which tries to do something of that sort and shows that if you're trying to jointly tune a retriever and generator, it improves both of them, both the retriever and the generator. Okay, so I will pause here. Any questions? Yes.
Okay. Do you guys have any multimodality coming in for the models?
In terms of this Granite 3.0 models, these are across different tasks still, but not like if you're thinking of image, no.
Okay. And any computer usage or something in the long run?
Computer usage as in?
As in, like, I think Claude came up with a demo a few months ago where they like let Claude use the computer through the GUI.
Oh, this is basically more towards the agentic stuff. So let's
Yeah.
say you are trying to answer something from Granite and you want to revise your answer by looking up internet for the
Yeah.
latest information around it, right? So this is more about creating agentic loops that uses Granite or any model per se and revises over it.
Yeah. Like, are you guys working on it or?
That's more of a agentic solution stuff than a model stuff. Yeah, we are.
Yeah. I mean, you have to fine tune it for it.
Deepti will be speaking about.
Another question is you talked about the fairness about IBM compared to like OpenAI and Meta everything. Like, can you talk about it in detail because it was just surface level?
Okay, so no, basically by fairness, what I mean is whenever we are releasing a model, if it is to be consumed by an industry for commercial purposes, it needs to satisfy certain criteria. For example, it needs to be transparent, it needs to use license-friendly data that you are free to use for commercial purposes. Those are the things IBM purposefully makes sure during its training. And it's very transparent. You can literally look at the model card and see what all data it has
So
gone.
the data which is trained on, like, is it available to watch, like read? Because is it listed
Granite
what
papers
on?
explicitly list all the data that it has
Okay.
used. That's part one. And the second part of your question is if you're trying to think fairness more towards removing racial bias or having nice guardrails put into it. So in Granite recipe, again, in the paper, if you see, they have given detailed steps towards what kind of synthetic data generation they did and the type of filtering they came up with to make sure that the data that they are training, it is devoid of those racial biases or the taxonomy I just spoke of.
Yeah.
It uses those taxonomy to filter out any kind of harmful content that can creep in there.
Okay, thank you.
So while Pankaj is setting up, I had a question. So
Yes.
you touched upon the transformer architecture, but what makes Granite models more efficient as compared to say Llama or?
Yeah, so I would say first is the data cleaning part. That is very important. It often go unnoticed. But if you have a clean data with lesser data, you will learn more. Okay. And then this Instruct Lab, which is also IBM's open source offering, it has a very nice way to navigate what kind of data you want to generate. And it can become more task specific. For example, if you are focused on enterprise kind of data, you would want to generate data which are more specific or more helpful towards RAG. And InstructLab lets you navigate those space much better. So what effectively means is even with lesser data, you are generating content that is more useful for enterprise.
So is it mainly to do only with the input data that it is trained on? And
much part of it that, but of course, I mean, and now it's taken over, but I had some detailed slide where literally you can see the different hyperparameters or the different types of embeddings that had been used. Some of the hyperparameter search has gone in and we have taken the best combination. But that I would say is a routine exercise in every LLM. Okay, that's not the exceptional part. Exceptional part is making sure the kind of data that you are using and the kind of data that you are generating to tailor it to a certain task. That's the differentiator for IBM.
thank you.
Yeah, more than enough. Am I audible? Yeah. Okay. So thanks, Jaideep. So Jaideep talked about two modalities, right? Language and code. So what I plan to cover is this another interesting modality which is very common and a lot of late there has been a lot of interest is this time series, right? So don't know, maybe many of you are already aware about time series and time series analysis, but let me briefly introduce the setting, right? So when we talk about time series, it's nothing but a sequence of data points that occur at given time granularity, and you observe it over some period of time, right? So that's what usually a univariate time series. And many a times the thing of interest for us is there are multiple such time series that can be observed, right? And there is correlation between, let's say, a value. See this red time series at different points, you're observing some values. So value at a given point may depend on what happened in the past, right? So there is some auto correlation in the time series. Likewise, value for the red series may also be dependent on the values, past values for some of the other time series, right? So there is cross correlation. So these are complexities that one who wants to, let's say, do some analysis of this time series needs to model it, right? And such type of data and applications are very common in core enterprise operations. For example, if you look at industrial settings, plants and equipment, there are a lot of sensors that are installed and you collect a lot of data at a minutely granularity or 5 minutes, 15 minutes, different data granularity, you collect a lot of data. And the thing of interest is for any plant operator is what can you do with this data? Can you gain some insights from this data and use that to either efficiently operate the plants in terms of how do you control the equipments, or you want to, let's say you get an indicator that, okay, something might fail, then you can take proactive actions of better decisions, right? So that's in an industrial setting. Likewise, in other domains like retail and supply chain, you again have a lot of time series data about sales and demand for a product, and that can be used to do better forecasts so that you can do a lot of planning around it, right? So various applications. But again, one thing I just wanted to clearly basically illustrate setting is that when we talk about multivariate time series, each of this series may be of a different type. So like you may have certain data which is outside the system that you're modeling that can be exogenous signal. So time series modeling or forecasting, what you are interested in is looking at the context, the past, you want to forecast what's happening in the horizon, forecast horizon, right? So this exogenous signals are something which it's outside the system that you're modeling. So you know the values in the past, and you have some other model that can also tell you, okay, this is how this variable will behave in the future, right? Likewise, there are signals or data which are like control signals, where you again know what are the control settings for the equipment in the past. You have that data, and maybe in the future also, based on what are your control operation strategies there, you know, okay, this is how I would like to control my equipment in the future. So some of these data may be available in the future horizon. And what's of interest is for some of this target data which you are trying to forecast, given the past context and the information that is available for the other variables, you want to know what is the forecast for some of these target variables, right? Likewise, you will also have conditional variables where you know only the data till the forecast point, but no information is available about the future. So you have different types of variables. And when you build any capability, ideally, which needs to be applied in different settings, you should be able to model all these type of variables. So what is a time series model, foundation model, right? So in traditional machine learning, you essentially for a given task, you would take the data, take the labeled data for that specific task, and you would build a model for just addressing that task. But similar to language LLMs and time series also, ideally, given a lot of unlabeled data that is available for a given setting, you may want to train a generic model that can learn some representation for that domain. And that model can be used for different types of tasks in zero shot, or maybe you can do some type of fine tuning, right? So that's what is about time series foundation model, a model that can learn a generic representation from a time series data, right? And such type of models, ideally, it helps improve the prediction accuracy if you are looking at forecasting tasks. And also, as you want to develop new models, right, for specific tasks, because you have a starting point, a pre-trained model, then it becomes much faster and easier to get a fine-tuned model for a task-specific fine-tuned model, right? So what is the difference between time series? Why do we need a separate model for time series, given that there's so much work happening in the language domain, right? So here we have listed down the key differences, right? So in language, when we talk about a language, each word has a semantic meaning, right? And it's largely same across, whenever you use the word across context, more or less it's the same, right? And mostly it is single channel. You have single sentence or a single channel that is being used to maybe summarize or do different tasks. And there is underlying grammatical structure that is similar, even though you're working across different domains, right? You have unstructured data in different domains, but the grammatical structure is more or less same. And a huge amount of public open data that is available. That's why you see this big language model, right? LLMs with billions and billions of parameters. On the other hand, when we talk about time series, a value at a single time step, if I look at any time series, any domain, just one value may not convey anything about what's happening, right? So you need to look at the context. And then as I discuss, many a times what you will have is multivariates, right? Multiple variables that you want to model, learn correlation within the series and across the series, right? And one other very big challenge over here is this data that you have, even what are publicly available data, or when we work with specific settings across different industry, they are very different in terms of time resolution. Some data maybe you have at hourly resolution with different seasonality. Other data maybe it's at minutely resolution or weekly resolution, right? So each data set comes at different time resolution, sampling rate, and scales. There are a lot of lags, drifts. So there are a lot of complexity that one needs to handle when building such models. And other important thing to notice is that the publicly available data sets to build such foundation model, they're not much, right? So very small publicly available data set is there. So that makes the task very difficult, right? So with that, I guess in previous session, you would have seen a part of this slide on how this evolution from big data and machine learning to LLMs. But what I want to highlight in past 2 years, 2023 and 24, a lot of focus on time series foundation models, right? Both transformer-based architectures and lightweight models from various organizations like Kronos from Amazon, Moirai from Salesforce. IBM has this state-of-the-art model. I'll discuss about it. Tiny time mixer, patch TS mixer is again architecture, foundation model architecture. So all these, a lot of development that has happened in 2 years, and in 2025 and beyond, what we want, what we are expecting is enterprise and use cases to basically use some of these models and derive value out of this, right? Yeah. So what are the benefits, as I mentioned? So pre-trained models. So once pre-trained model, essentially, let's say you are looking at industrial setting where the organization may have multiple plants. Then you can take all the data, even though it's unlabeled, you can take entire data, train one time, you can have a pre-trained model for that domain. And then you can do targeted fine tuning. If you are interested in a given plant, which may have a different capacity and different type of equipment, start with a pre-trained model and then do limited amount of fine tuning using that plant specific data, which can be used for different types of downstream tasks. So it allows for quick scaling and less parameters are involved in training this. Then prediction horizons can vary. Let's say you can have a short-term prediction from, let's say, 96 data points to 196 or long-term prediction, right? And reduced amount of effort is required, because when you talk about time in traditional machine learning, you do a lot of feature engineering is involved and a lot of manual effort is involved. Here, there is no feature engineering. You just take the pre-trained model, pass the data for the new domain, and it can be used for both zero shot as well as fine tuning and getting the forecast, right? So in a typical, this slide basically talks about what's a typical workflow, right, for different types of tasks, right? So the first workflow is for pre-training the model. You start with a time series, you do some type of pre-processing, aggregation, normalization of the series, tokenize it. So what we do is we patch. There's something called as patching. So nearby sequence of points, let's say 10 points, I define a patch, you tokenize the time series, and carry out the pre-training to get a pre-trained model, do some hyperparameter tuning to get a pre-trained model. And once you have a pre-trained model and you have, let's say, asset-specific data, two workflows. One is you can use it directly in zero-shot inference. But let's say you want to do some type of fine-tuning, you take a asset-specific data, do some fine-tuning with tuning some last layers of the model, and then do the evaluation and use it for different types of tasks. The tasks can range from forecasting to classification, regression, anomaly detection, right? So in anomaly detection, maybe you want to detect anomalies in different process behavior of interest, right? This can be point anomalies or sequential anomalies. Forecasting of system for certain KPIs of interest, you want to do a forecast for a future horizon. Also prediction of control, right? So you want to predict like what will happen to the KPIs if I apply certain control settings, right? So it's more of what if type of analysis. What if I change control variables for equipment in certain way in next few hours? What will happen to my forecast, right? And classification clustering. So these are different types of downstream tasks that are supported with these models, right? So at a high level, as I discussed in the previous slide, there are two steps. Start with the pre-trained data, train the given architecture, train a model for a pre-training task. The pre-training task can be a reconstruction-based task or a forecasting-based objective. Based on that, you get a pre-trained model. Then given a task-specific data, once you get the representation from the model, you can fine-tune the head for different downstream tasks, can be forecasting, classification, regression, right? So this is at a high level, the steps involved. So now this slide essentially talks about our journey, right, in time series foundation. So far we have discussed about what is time series foundation model, how pre-training, fine-tuning works. This has been our journey in this space. So we started with transformer-based architectures, TST and patch TST. And later we moved to lightweight foundation models with MLP mixer-based architecture. So patch TS mixer, which was published last year, auto mixer, and this year we have this in NeurIPS, we have this tiny time mixer, a very lightweight time series foundation model, pre-trained model with 1 to 5 million parameters. And this is released on Hugging Face, so anyone can go on Hugging Face and try out this model for different types of applications. And there has been huge interest in these models, right? Where already there are 2 million plus downloads and people have given a lot of positive feedback about this model, right? So how does this model work? So with this example, I just wanted to explain, let's say you want to do a zero-shot inference using these models, right? So how does it work? So this example is for energy demand forecasting use case. So we have access to 4 years of hourly energy consumption and generation data for Spain. And there are like this energy consumption and generation is also dependent on a lot of exogenous features like weather across several cities. And the problem of interest over here is given the context, whatever you observed in the past, the energy consumption and generation, can you forecast for next 96 hours, what would be the demand for electricity, right, or energy? Right? So what we have done over here is we have tried out different workflows. So one is we have leveraged pre-trained tiny time mixer TTM model, which has been pre-trained on publicly available data set in zero-shot manner. We have provided the context, the historical data of past 512 hours, what has been the energy consumption. And based on that in zero-shot manner, this is this TTM base, light blue color, we get what is the forecast for next 96 hours, right? So you see it's very close to the ground truth. And the one in white is the statistical model, the standard statistical model that is used to generate the forecast. So some of the peaks, the statistical model is not capturing well. So now if you do take a small amount of data for this specific use case and do a limited amount of fine tuning and also include some of the exogenous features like weather, cloud cover, other features, then the performance of TTM fine-tuned model is slightly better than the zero-shot model. So where it's capturing some of these peaks very well, right? So in terms of metric, if you look at RMSE, the fine-tuned model has a much lower RMSE, lower the better. So has a lower RMSE as compared to the zero-shot model, which does very well as compared to the statistical models, right? So overall, I mean, key thing to observe is that it's able to capture the seasonal pattern even in zero-shot case, right? It has not seen this data in zero-shot, it's able to capture some of these patterns. And both zero-shot and fine-tuned models are performing better than some of the other statistical baselines, right? So that was example of, okay, given a new data set, I have limited amount of data set, I want to use a pre-trained model just for that data set in a zero-shot or do fine-tuning, right? This is something we are doing internally for IBM, where we have large amount of data for IBM flash storage, where a lot of data on this IT ops, IO ops data in terms of different KPIs or metric that has been captured. And what we wanted, because we have huge amount of data for this domain and it's in a standardized format, we wanted to basically, instead of going for a general pre-trained model, using the same architecture, whatever is there behind the scene for TTM, tiny time mixer, we are training a domain specific model for this domain, right? For storage domain, given huge amount of data that's already collected, use the same architecture and have a domain specific foundation model trained, right? And see how this model essentially, once you pre-train it on a domain, use it for different types of tasks. Like you want to do capacity forecasting. Given that whatever capacity has been used in the past, can you tell, okay, what would we project the capacity for next 6 months to 1 year, right? You want to do performance forecasting for different KPIs in terms of CPU utilization, latency, or other KPIs, right? Or any deviation in performance you are observing, any change point or deviation in the performance, right? So these are different types of fine-tuning tasks or different tasks that needs to be supported for this product. So we have taken the same architecture, basically pre-trained a model using data for nearly 30,000 devices that are being monitored. There are 350 plus KPIs sampled at 5-minute frequency, right? And we have leveraged as I discussed, the architecture that was used for TTM, the patch TS mixer architecture for pre-training. And these are not the complete results, just some initial results on when we pre-train the model and compare it with some of the existing ones that the team is using, we get huge improvement in terms of performance. And also because these models are very small, so there is, if you look at the inference time, zero-shot inference time, this is also much less as compared to the traditional statistical models, right? Fine-tuning also is pretty fast. So our focus has been on lightweight model architecture and lightweight models so that some of these inference and everything is done very efficiently, right? So this talks about, in general, for publicly available community accepted benchmarks, where does TTM stand as compared to some of the models that are there from the competitors, right? So we have several models from competitor, like Kronos is from Amazon, AWS, Moirai from Salesforce, Times FM from Google. So as compared to these models in terms of parameters, our model is very small. So it's just 1 to 5 million parameters, whereas Kronos, if you see, it's almost 800, 700 million parameters, right? So these are very, very small models as compared to most of the other models. And for different types of forecasting tasks, like long horizon zero shot forecasting, or short horizon zero shot, where the horizon is very short, the forecast horizon, or few shot with using 5% data, you fine tune and do the forecasting. In all of them, the performance is much better than some of the other model. Like for long horizon forecasting, the Times FM from Google, it's almost 25% more error as compared to mean square error as compared to what you get from TTM, right? So both in terms of performance as well as the size, the model is very small and provides state-of-the-art performance. So this is what is accepted in NeurIPS 2024. And in terms of pre-training, right, this model essentially has been pre-trained on several data sets across different domains, right? So you have data set from energy consumption, generation, environment, Bitcoin, US, so diverse data set, and then novel techniques that are used while pre-training the model. So we have something called as MLP mixer-based architecture. We do adaptive patching of time series because this data comes from different domains which has different seasonalities. So we do adaptive patching and then prefix tuning to address this heterogeneous data. So a lot of, so more details you'll find it in this paper, and if there's more interest here, we can have a discussion around this, right? So in terms of inference time, CPU inference time and model size, again, as I mentioned, the models are pretty small, and so that gets reflected in the inference time as well. So this is where TTM stands as compared to most of the other models, where in terms of size and as well as the inference time, they are much worse as compared to TTM, right? And these are some of the useful links if someone wants to try and play with these models. So all these models are available on Hugging Face. And there are cookbooks and recipes available to carry out basic inference or do some fine tuning with some examples, right? So I'll quickly take you through some of the. So this is the model card where you have details about model, the description, what type of models we have released. So we have released 3 models over here. Model that works with a forecast horizon of 512 and the context of 512 and forecast horizon of 96. Then we have one more model with 1024 and 96 and 1536 and 96. So three different models. But we have a routine that helps you, given a data, it can automatically select which is the best model, do zero padding and apply it for inference, right? So all those things are available. So this get model utility essentially automatically selects the required model. So in terms of capability and examples, you have a getting started collab notebook is there. Then if you want to do zero shot multivariate forecasting, you can refer to this example. Fine-tuned multivariate forecasting. So there are various examples and notebooks that we have released, right, with for different types of use cases. So that will help any developer or anyone who wants to experiment with this, that can help anyone get started, right? So benchmark scripts, how the benchmarking was done. So all the details are available on this model card. And then let me show you the recipes and cookbooks, right? So as we speak, we are adding different recipes for different domains, right? So the plan is to, by end of, in next 3 months, at least have 20 recipes for different domains, right? That would help people get started, right? So this is the recipe, as I said, right now there are 4 recipes. So let me show one of them, right? So this is energy demand forecasting. So you can install all the notebooks from the public repo, import the required packages, point to the data for which you want to do the zero-shot forecasting. Just specify which is your time column and which are the target variables that you want to forecast, right? Once you specify this, then I guess, yeah, this is simple. I mean, yeah, just normal plotting of some of the data. And then you call this tiny time mixer for prediction routine, the zero-shot model, where we use TTM R2 release and provide the input channel, what needs to be forecasted to get the zero-shot model. And we have this tiny time series forecasting pipeline. So this pipeline essentially creates the forecasting pipeline, and then you can call the zero-shot forecast, right, using this model. Finally, I mean, yeah, you can plot the predictions and then see how the model performs in zero-shot manner on the new data set, right? So this is a very simple basic notebook. So likewise, we have notebooks where you can play with exogenous variables and different things that I discussed, right? Control or exogenous variable or do fine tuning, right? So yeah, I would encourage people to, yeah, all of you to go look at these notebooks, try it out and provide your feedback, right? Any inputs on this would be appreciated. Yeah. And of course, you can contribute to this. This is an open source project, so any contributions. Okay, thank you. Any questions?
I had a question. So must be difficult to get tagged data for a time series, right? As against, say, the language models where the language structure itself is tagged. So how do you deal with that? And also, do you also correlate it with, say, non-time series data in a like something similar to RAG or other ways?
Yeah. So yeah, to your first question, right? So there are a lot of unlabeled data that is available. And pre-training the type of task we use is because the data is mostly forecasting objectives. So you have a time series data where you know, given a context, you already know what's there in the future, right? So with forecasting objective, the time series data already is available, right? Unless you are working on, let's say, class failure or something, classification type, their labels are limited. That happens during the fine tuning. But to learn the representation for a given time series, where you want to look at seasonality trend, there are two different ways people do it. One is reconstruction based objective, where given a time series, maybe you mask something and want to reconstruct, right? Using you encode it and try to reconstruct the same time series. Other is with forecasting objective. Given the past, you want to forecast the future. So you take a historical time series, do patching and create this XY pair where X is your context and Y is your forecast. So there you don't need label, right?
Right. Actually, yeah, sorry, I forgot to mention, I meant the anomaly detection part or anomaly prediction part.
Oh, anomaly predictions. Okay, so anomaly is a downstream task. So there, I mean, once you have this time series and as I said, the reconstructed signal, you look at the deviation of the reconstructed signal from the actual time series. And then on top of the error, you apply some, maybe for sequential anomaly, some techniques, or you have a different scorer or detector on top of that. But in order to validate it, you will have to then adjust some fine tuning of the threshold that needs to be done for anomaly detection. Classification also, you have a classification head with limited amount of labeled data for a domain. You can tune the parameters to basically get the classification working. But the pre-training, which is the main objective for this pre-trained model to learn the representation, that can be done on what a huge amount of unlabeled data across domains. So that's the advantage. Yeah.
Visualization tool to see what has actually learned because it's a time data.
Yeah. Yeah. Yeah, there's gated attention layer. So we have some in the paper, if you see, for different data sets, it has clear separation in saying that, okay, this type of data with certain seasonality and pattern in the embedding space, there is some separation you observe, right? So that helps at least get some intuition of, okay, it's learning some representation where data from maybe energy domain is maybe represented somewhere else. So there is some separation we observe. Right? question
So
there. Yeah.
I wanted to ask, like, in generally, what I seen in time series is the way you process your data before you apply any time series model is actually very important. Like, so like you didn't discuss any of the like how did you process that data, or like is it specific? So for example, what normalization did you use, or like is there any specific type of time series? Like for example, if the time series is just too much up and down kind of thing, so this model kind of their result kind of vary a lot depending on the nature of the time series.
Yeah. So for normalization, right, we use Revin. Revin is used for normalization and feeding into the, before getting into the model, right? The encoder and decoder, right? So that's the standard thing that is used. So before feeding any zero shot, you do standard scaling and feed to the model to get the inference. Now, your question on data which has huge noisy behavior. So predicting those things are usually in a time series forecasting, you may end up predicting the mean behavior, right? You may not be able to get. So that is typical challenge that anyways is there in forecasting tasks, right? So you cannot predict, and what a signal is there, at best you can try to forecast or get the signal, right? But if you want to basically process this, maybe you can do some type of smoothing before feeding the data into the pre-trained model, right? But for us, we have not done any type of pre-processing. So what a publicly available data set is there, we took those data set as is, did some normalization and fed into the model for.
So no access to get wrong.
Nothing was, yeah, no. But yeah, so multi-resolution sampling was done for the data set because we had data set like 1 billion data points that are used for training the model. Now, in order to increase the size, we did multi-resolution sampling of the data. So same data, maybe you sample it at different frequency to increase your overall data that gets into the model.
You got some geospatial models posted on your Hugging Face. Could you brief them about this?
Yeah, there's a separate team who is working on geospatial foundation models. So Prithvi is one of the models that has been released.
Yeah, there's a bunch of models over here
Yeah.
with like
So
separate versions of
unfortunately,
it.
anyone has no, I don't have much information about, I mean,
Yeah,
those
sure.
models
If you
that I use, but we can share more paper details of. He wants to know more about the geospatial model that is. Yeah. We can point you to the paper. Right?
Sure, thank you.
There is an online question. So, does adding knowledge graph improves the inference of TSFM?
So, okay, so for domain specific models, right, many a times what happens, as I said, the model has to learn control, response to different controls. So if there is certain knowledge which is not reflected in the data, it's very sparsely there in the data, not captured in the data, right? So the model, it's basically a data-driven model. So it will not learn the response for those controls. So there we are working on some ways of infusing this, guiding the model, right? Or infusing this knowledge in terms of augmenting more data that reflects, that captures that knowledge and using it for training the model so that that behavior can be captured. So many a things which cannot be learned by data-driven approach, and if there is underlying knowledge graph that basically captures that domain or process, then how do you augment more data and infuse it while fine-tuning the model? There's a lot of work we are doing. But it's a very good question. Yeah, that's very important in fact. Yeah.
Thank you. That's it.
Thank you. Thank you. Yeah, if it's multivariate, then I guess channel. That is if it is not 5 internally it will but now we are releasing model that can basically work with any general context. Any context you user can provide. Let's say you have data for your domain, maybe just 100 context. It will make sure you use the right product. Then what are 100 context is given.